Hello, this is Dr. Liu. In this video, I will discuss what is a centripetal force. So let's just review what exactly is a centripetal acceleration. So here I have a circle, and it's not very circly, so let's try to amend that. Maybe get rid of this half. Oh, I see. Okay, so if an object is bound to travel in this circle, whatever it is, could be the moon traveling, orbiting our planet Earth. So there has to be this acceleration because the velocity keeps changing. So at this moment, it is in this direction, and the next moment, it has to change direction to always stay tangential to the circle. So that's a new velocity, right? And it would require an acceleration always pointing toward the center to achieve that. So if there's an acceleration, there must be some net force that caused the acceleration, right? We have this acceleration equals v squared over r, or we also introduced angular velocity omega squared times r, if the object experiences uniform circular motion. Okay, so this is the result of a uniform circular motion, and we call this a centripetal. Okay, so if there's an A, then that implies there is a net force. So we can say that net force that caused this acceleration will be linked to mass times acceleration, right? So if we simply take this formula and plug it in, we have mv squared over r. Or if we take this formula, we get m omega squared times r. And this net force causes the object to travel in a circle. So we just define this. That means equivalent, three lines. We define this as centripetal force. And this force is not yet another force apart from the forces we're more used to, such as gravity or normal force from surfaces or friction or tension. It's not yet another force, it's just the net force. So it depends on the situation. Sometimes tension alone is acting as the net force. So let's just say that you swing a ball. So you swing a ball in more or less a horizontal fashion. So this is a top view of you swinging a ball. So this ball travels, and it would require a centripetal force toward the center in order to have this acceleration, right? So what is this centripetal force? And in this case, this is just tension, or sometimes I write Ft. So this is a physical string here that you pull. So the string, you pull the string's end right here, and the string will pull the ball, right? So this is swinging a ball. Okay, let me just rewrite that. Okay, so you swing a ball. But if you consider gravity, then gravity pulls the ball down. So this line is not exactly horizontal. It has some vertical component, but that doesn't invalidate the fact that part of tension is still acting as the net force, right? So in this case, it's just one force, one physical type of force is acting at the total net force, and that is the centripetal force. In another case, it could be the Earth and the Moon, right? So here's the Moon, the center is the Earth. So there's no string, but there's still an attachment. Well, that's due to universal gravity. So this force, we can call this F capital G. So this is universal gravity. So in this case, the moon's centripetal force is from this universal gravity. So Earth and Moon. Okay, so there's another example I'd like to go through. This is actually a side view of a roller coaster. So there's quite a large loop here, and let's just say we have roller coaster cars. So there's maybe 5 of them. I'd like to have a middle one. Okay, so they're going this way up the loop. So at the moment, this middle car here feels gravity, right? This is not toward the center. Here's the center, but there's a normal force pushing up, supporting the cart from the tracks. So this normal force is not the centripetal force, and this gravity is not the centripetal force either, but the net force, which is normal force minus gravity. If this roller coaster cart is going at a uniform speed at the moment, at least, and this will be the net force, the centripetal force. So as you can see, the centripetal force is not yet another force. It is a combination of all existing forces that cause the uniform circular motion. So as now let's just imagine as the roller coaster car go to the top, and now we're actually upside down. So yeah, a lot of screaming going on. Okay, so now this middle cart, what happens? Gravity pulls down. Okay, so all right, and there's also some normal force because these roller coaster carts, they're the wheels and the tracks, they're kind of locked together. The tracks can hold these cars even if the cars are inverted. They're upside down. The tracks can still hold. So over here, it depends on the speed. There could be some normal force upward, or if it's too fast, normal force could be pointing downward to provide enough centripetal force. Right? If you inspect the centripetal forces formula right here, if the roller coaster car is really fast, it would need a lot of centripetal force. What if its gravity is not able to provide all that? Well, then the normal force will have to point down and add to gravity, so that the total will be enough to sustain a certain speed. But if the speed is low enough and the gravity is more than enough, then normal force can still point up, so that the difference always is equal to this. Thanks.